Muy buenos días a todos. Mi nombre es Luciano, soy de la Secretaría de Posgrado de la Facultad de Ciencias Exactas de la Universidad Nacional de La Plata. En este caso, estamos en vivo para la defensa de tesis doctoral de Martín Lagares. Esta defensa de tesis será defendida, será dictada en inglés. Así que les aviso por eso. Martín, muchos éxitos.
Okay, let's begin. So my name is Martín Lagares. Today I will be presenting the work I did during my PhD. My PhD thesis has a title which is Line Defects and Scattering Amplitudes in the context of the ADS-CFT correspondence. So first of all, I want to thank Diego for supervising the work of this thesis. I want to also thank Silvia, Francisco, and Pedro for accepting being members of the examination committee of the thesis. Before beginning, I just want to mention that the work that I'm going to present in this presentation is based on the following publications, which I did with Diego, with Johannes, who's in the audience, with Victor Gerardo Rivera and Ignacio Salazar Landera, who are probably also in the audience, with Gabriel Villar, and with Shunkin San. So let me start with a brief outline of the presentation. I will begin with a short motivation of the work. Then I will move on to describe the properties of line defects in ADS-free CFT2 dualities. Afterwards, I will discuss the integrability properties of line defects in the AVGN theory. And then I will talk about integrating net geometries in the AVGN theory. Finally, I will give some conclusions and discuss future directions. So let's start then with the motivation. So in the past century, we have seen remarkable progress in our understanding of quantum field theory as a precise model of nature. And this is exemplified in the outstanding agreement that we have seen between the theory and the experiments. However, much remains to be understood about quantum field theory. And for example, two of the main current challenges that we have in PFT are to develop and refine non-perturbative methods and to understand the properties of scattering amplitudes and to develop efficient tools for the computation of scattering amplitudes. So the overall goal of this thesis was to try to contribute to these ongoing efforts. So regarding the first one, we know that despite the many advantages that the perturbative expansion of observables in QFT has in terms of Feynman diagrams, the computation of the Feynman diagrams quickly becomes infeasible. So, for example, computing 3 or 4 loop diagrams becomes quickly very difficult with the current tools that we have. So, a very valid question that we can pose in this context is whether we can bypass the explicit computation of Feynman diagrams through the use of non-perturbative methods. And I want to remark that progress in this direction is crucial to understand the low energy dynamics of quantum chromodynamics, which we know that is strongly coupled in the IR. So a very interesting framework to study non-perturbative methods was proposed by Juan Maldacena a bit less than 3 decades ago by his proposal of holographic dualities between string theories and some CFTs. So the most renowned example of an holographic dualities was proposed by Maldacena, and it's the duality between type 2B string theory in ADS5 times S5 and the 4-dimensional n equals 4 super-Yang-Mills theory with UN gauge group and SU4 R symmetry. So one of the most remarkable properties that this correspondence has is the way in which it relates the coupling regimes of both theories. Because we have that the strong coupling regime of one theory is mapped to the perturbative regime of the other. So in this way, we can apply a non-perturbative method in the CFT, for example, and then test the result of the non-perturbative method as strong coupling with weak coupling perturbative expansion in the string theory. So, as I said, this is an ideal framework to develop and refine non-perturbative methods. So another interesting duality that we have is the duality between N theory in ADS4 times S7 quotient ZK, which in the top limit becomes type 2A string theory in ADS4 times CP3, and the 3-dimensional AVGN theory with UN times UN gauge group and Chern-Simons of ZK. So because this theory is going to be important in the rest of the presentation, I just want to mention briefly the matter content. So we have 2 gauge fields in the adjoint representations of the gauge groups, and we have 4 complex scalars in the fundamental representation of SU4, the R symmetry, and in the B-adjoint representation of the gauge groups. And we have also 4 Dirac fermions in the fundamental representation of SU4 also, and in the fundamental representation of the gauge groups. The action is schematically shown here. So we have the Chern-Simons term for the gauge fields, the kinetic term for the matter fields, the scalars and the fermions. Then we have a quartic interaction term for the scalars and the fermions, and a term of order 6 for the scalars. So again, this duality relates the strong coupling regime of one of the theories with the weak coupling regime of the other, and is therefore, again, a very nice framework to study non-perturbative methods. So a very appealing object to study these methods are line defects in the context of holographic dualities. And the most canonical examples of line defects are the 1/2 EPS Wilson line of equals force Bayes Mills, which can be defined as we show here with the allonomy of a gauge connection along some contour plus some coupling to a scalar of the theory. So if we take this coupling to be constant and the contour to be a straight line or a circular contour, we get that this operator preserves 1/2 of the supersymmetries of the theory, and therefore is 1/2 EPS. Similarly, we can consider the 1/2 EPS Wilson loop of ABJM, which is constructed in terms of this UN/N superconnection. We have both bosonic couplings and fermionic couplings. So if we take the couplings to the scalars and the fermions to be, as we see here in the slide, we get that with a straight contour, the operator is again 1/2 EPS. We can also take a circular contour with similar couplings and get a 1/2 EPS operator. So let me now tell you how, in which sense these operators define one-dimensional CFTs. So if we consider the insertion of operators along the contour of the Wilson line, and we take the expectation value of these insertions times the Wilson loop operator, and divide it the expectation value of the Wilson loop without the insertions, we get that this quantity effectively describes the correlator in a one-dimensional conformative field, which is a one-dimensional defect CFT. And there is a very interesting and useful set of operators that are defined due to the breaking of the supersymmetries of the bi-CFT because of the presence of the defect. The most canonical example is the displacement operator, which arises from the breaking of the translation symmetry. As we see here, we have this conservation log with a source term, and here the source term defines what is known as the displacement operator. Similarly, we can consider the breaking of the R symmetries or the breaking of the supersymmetries, and this again defines operators. And usually these operators lie within a same supermultiplet, which is the displacement supermultiplet. So a very remarkable and useful properties of Wilson lines and line defects in ADS-CFT, which makes them very appealing for studying non-perturbative methods, is the fact that they have a very well-prescribed holographic dual. So the dual of the Wilson line is an open string which ends along the contour of the Wilson line in the boundary of ADS. And more precisely, we get that the expectation value of the Wilson loop operator is equal to the partition function of the dual string, which in the supergravity limit can be safely approximated by the exponential of the minimal area of the dual string. In this context, we get that the operators in the displacement supermultiplet can be identified with the transversal fluctuations around the dual string. So, as I said before, line defects pose a very interesting laboratory to study and develop non-perturbative methods because of the low dimensionality of the CFT that they define. And this is exemplified in the very vast literature that we have for this kind of studies. For example, if we consider analytic confounded bootstrap methods, in the case of the N=force Bayes theory, this can be applied to study of 4-point functions along line defects by Lienda-Meneghelli some years ago, and then by Ferreira-Meneghelli and many other authors. The extension of this to 6 points is yet to be developed. There has been some recent progress in the weak coupling limit, but a more complete formulation is yet missing. This has been also extended to ABJM at 4 points by Lorenzo Bianchi and collaborators. Again, in this case, the extension to 6 points is yet to be developed. We can also mention integrability methods, which were initially described in the context of line defects in ADS-CFT by Drucker and Kawamoto in 2005. And then in 2012, in a series of 2 coordinated papers by Drucker, Diego, Balacena, and Siever, thermodynamic Bethe-Ansatz equations were applied for the description of the Kasparov dimension of the theory. A few years later, a quantum spectral curve formalism was proposed for the line defects of ADS-CFT, in particular for the 1/2 BPS line defect, by Collier-Gromov and Lekovic-Matthew. In the case of ABGN, up to the beginning of this thesis, there was no TVA approach for line defects in the ABGN theory. And this is one thing that we study in the context of this thesis. A quantum spectral curve formalism is yet missing in this case. We can also mention bootstrapability methods that very nicely merge the numerically conformal bootstrap methods and the integrability techniques. These were first developed by Andrea Cavaglia, Collier-Gromov, Julius and Michelangelo Preti in a series of papers. In ABGN, this is not yet developed because we are lacking a QSC formalism for the BPS lines. Let me also mention supersymmetric localization, which was a method initially proposed in a seminal paper by Pestun and then studied by many authors. This was also extended to ABGN theory by Kapustin, Willis, and Jacob, by Drucker and Rancanelli, and by Silvia and many collaborators. So from this table, we can see that there has been many developments for the study of line defects, and in particular for non-perturbative methods in the context of line defects in ADS-CFT, in ADS5 CFT4 and in ADS4 CFT3. But we can ask, what about line defects and non-perturbative methods in the context of ADS3 CFT2, which is a much less studied duality? And as I said, can we apply integrability methods to the description of line defects in ABGN? So this leads us to the first 2 goals of this thesis. The first one was the study of the existence of BPS line defects in ADS3 CFT2 dualities, and to see whether we could apply analytic conformal bootstrap methods for the computation of correlators in these defects, and the study of whether integrability properties could be applied for the description of the 1/2 BPS line defects of ABGN, and to see whether we could derive TVA equations to compute the Kasparov dimension of the ABGN theory. There is a third goal also in this thesis, which I'm now going to introduce. So another current challenge in QFT is, as I said, the development of efficient tools to compute scattering amplitudes. These observables are very important because they directly contribute to the cross-sections that we measure at the LHC. And a very interesting property of scattering amplitude is that despite usually we need hundreds of time endurance for their computation, for the perturbative computation, in the end, the result is often remarkably simple. So, for example, we get the Parks-Taylor formula for the 3-level scattering MHD scattering amplitude of the gluons, which requires hundreds of time endurance for the computation, for the perturbative computation. But in the end, we see that the result fits within a line. So we can ask, how can we understand the simplicity of scattering amplitudes? So an important step forward in this direction was provided by Nimar Kaniamed and Gerald Trinka a bit more than 10 years ago, with the proposal of a geometric approach to describe scattering amplitudes in the N=4 field theory, and this was later extended to many other theories. So one of the key ingredients of the proposal is that the L-loop integrands of the scattering amplitudes in N=4 field mills can be described in terms of a volume form of what is known as a positive geometry, which in the case of N=4 field mills is known as the amplitude hedron. So a positive geometry is a projective variety that has a unique volume form, which is known as the canonical form, with logarithmic singularities at the codimensional 1 boundaries, and it's such that each of these boundaries is again a positive geometry. So the simplest examples of positive geometries are the line segment, whose canonical form we see here, and which satisfy all the axioms that I listed above, and the triangle, whose canonical form we also see here. So before continuing, let me just make a very brief parenthesis to introduce some notation for the kinematics of scattering processes of massless particles in 4 dimensions. So to describe the kinematics of these processes, we can either use spin or helicity variables, which are these lambda tilde and lambda variables that we see here. We can also use dual space coordinates, which are essentially the difference between 2 consecutive momenta. Or we can use momentum twistors, which were introduced by Hodges some years ago, which are defined via these incidence relations between the lambda spin-off helicity momenta and the dual space coordinates, and are such that points in dual space are identified with lines in momentum twistor space, and likewise lines in dual space are mapped to points in momentum twistor space. So, for example, we get that the loop momenta is mapped to a line in momentum twistor space. So a very interesting property of momentum twistors is that we can very easily construct invariants under the dual conformal symmetry of amplitudes in n equals 4 superior mills. This dual conformal symmetry is a symmetry of amplitudes in dual space. It's a conformal symmetry of amplitudes in this space. So we can construct the invariants under this symmetry by taking these 4 brackets between momentum twistors with the epsilon Levi-Civita tensor. So one of the simplest amplitude geometries is the 4-point L-loop amplitude, which is defined via these constraints that we see here. So the first 3 lines define a 1-loop amplitude geometry for each of the loop lines, and the 4th line are the positivity constraints between each of the loop lines. So we can pictorially represent this via these graphs, where each black node is a 1-loop geometry, and we get that the positivity constraints are represented by dashed blue lines. So, for example, this is a 4-loop amplitude geometry. But also proposed by Johannes, Nima, and Jared Blatt some years ago, it's very interesting to consider negativity constraints between the loop variables. And this is very useful because it allows us to very nicely represent the L-loop integrand for the logarithm of the scattering amplitude. And we can represent this L-loop integrand for the logarithm of the amplitude by taking the sum over all possible connected negative geometry diagrams with L-loops. And a very important corollary of this geometric description is that if we perform now all but one of the loop integrations over the L-loop integrand for the logarithm of the amplitude, we get an infrared finite object, which is known as an integrated negative geometry. These objects have been very much studied over the last years, and a very important property is that we can use them to compute the L-loop contribution to the Kasparov dimension of the theory by just performing L-1 loop iterations. And this was, for example, used by Johannes some years ago to compute the 4-loop Kasparov dimension of n equals 4 superior mills and QCD by just performing 3-loop iterations. So a question that we can pose is whether we can extend these ideas to the AVGN theory to compute the infrared finite integrated negative geometries of AVGN and to study the properties of these objects. So this takes us to the third goal of the thesis, which was to compute integrated negative geometries in the AVGN theory to study the properties of these objects and to use the integrated negative geometries to compute the Kasparov dimension of the theory. So we now move on to the second part of the presentation, which is a description of line defects in ADS3 CFT2 dualities. So in the context of this thesis, we focused on ADS3 CFT2 realizations in which the supergravity background is given by ADS3 times S3 times S3 times S7 metrics. Here, this omega parameter calibrates the radius of the 2 spheres, and a very important feature of these backgrounds is that we get a mixed free-form flux, because we have both Ramon free-form fluxes in the first line, and the Schwarz fluxes in the second line, and we get this bar theta parameter, which takes values between 0 and pi/2, and interpolates between pure Ramon and pure Schwarz backgrounds. An important limit of these backgrounds is when we take omega going to pi/2, because in this case the geometry becomes ADS3 times S3 times T4, and this is the limit that we will study in this presentation. So the first thing that we wanted to do was to study whether there are BPS strings describing BPS line operators in the dual CFT. So we did this first by solving at the classical level by solving a kappa symmetry equation, and we found that there are 1/2 BPS strings with Dirichlet boundary conditions that describe 1/2 BPS defects in the dual CFT. These strings are tilted with an angle that is proportional to this bar theta parameter that interpolates between pure Ramon-Ramon and pure Neue-Schwarz backgrounds, are perpendicular to a boundary in the pure Ramon-Ramon case, parallel to a boundary in the pure Neue-Schwarz case, are fixed at a point in the compact space, and therefore they have Dirichlet boundary conditions, and have an ADS2 induced metric, except in the pure Neue-Schwarz case, in which the metric is flat. So we also studied these strings at the level of the fluctuations around the classical solution, and as expected, we found that we can construct a set of 1/2 BPS Dirichlet boundary conditions for the fluctuations. So we also studied whether we can find more BPS strings by this classical analysis and the study of the fluctuations around classical solutions. And we found that there is a very vast set of BPS strings describing BPS line operators in the dual theory. So for example, we can construct smear strings by taking sets of Dirichlet strings that set on some submanifold M of the compact space and share some subset of the supersymmetries, and then taking the average of the partition functions of these Dirichlet strings over this manifold M. So this smear string preserve these subsets of supersymmetries that are shared by the Dirichlet strings. So by taking M to be different combinations of very great circles, we obtain 1/2 BPS, 1/4 BPS, or 1/8 BPS smear strings. Similarly, we can consider Neumann boundary conditions by fixing the normal derivative. By fixing this normal derivative along some combinations of great circles, we again obtain 1/4 BPS or 1/8 BPS Neumann strings. We can also consider interpolations between all these supersymmetric considerations to describe interpolating line defects, supersymmetric line defects in the dual CFT. So from now on, I will only focus on the 1/2 BPS line defect in the case of the ADS3 times S3 times T4 background, and I will describe how to apply analytic component bootstrap methods for the computation of correlators in this defect. So in this case, the back CFT2 is invariant under a PSU2 1,1/2 square supersymmetry and has an SO4 times U1 automorphism. And the presence of the line defect breaks the supersymmetry to just one factor of the PSU2 1,1/2 algebra and an SU2 automorphism. So we get that in this case, the symmetry algebra has 4 Poincare supercharges. And I want to remark that here the absence of the known Lagrangian description for the pi CFT2 for arbitrary values of the parameters of the supergravity background motivates the use of bootstrap techniques for the study of these line defects, because bootstrap allows us to bypass this absence of the Lagrangian of the CFT. So these analytic component bootstrap methods rely on, the main philosophy is to try to compute the CFT correlators by imposing symmetry constraints and other consistency conditions. And as I said before, these were applied to a study of the 4-point functions of insertions along the 1/2 BPS Wilson line of n equals 4 to Mills and the ABGN theorem. So let me just remark that for the case of the 1/2 BPS Wilson line in n equals 4 to Mills, we get that the defect preserves A supercharges. In the case of the 1/2 BPS Wilson line of ABGN, the defect preserves 6 supercharges. And here's where the 1/2 BPS line defect of ADS3 CFT2 comes to the scene, because it preserves only 4 supercharges, and therefore poses a very interesting setup to study whether we can apply analytic component bootstrap techniques to backgrounds where we have less supersymmetry with respect to the literature. So we study in this context the displacement supermultiplet, which arises from the breaking of the supersymmetries of the back CFT2 because of the presence of the defect. As we see here, for example, the breaking of the translation symmetry defines the displacement operator, and the breaking of the R symmetry defines the superprimaries of the displacement supermultiplet. Then we have 4 fermions, chi-fermions that arise from the breaking of the supersymmetries. We can also consider the breaking of the automorphism symmetry, which defines the tilt supermultiplet. In this case, we get 4 fermions as superprimaries and 4 scalars as superdescendants. So the first thing that we did was to apply the constraints that come from supersymmetry. And these constraints tell us that we can get all possible correlators between the fields in these supermultiplets by just computing the correlators of the superprimaries of these supermultiplets. And moreover, supersymmetry tells us that we just have to compute these 3 constants that are shown here in red and these 4 functions of the spacetime cross ratio to get the full correlators of the superprimaries of the displacement at this supermultiplet, and therefore to get all possible correlators of these supermultiplets. So let me stress then that we only have to compute with the bootstrap 3 constants and 4 functions of the spacetime cross ratio chi. So at link order, the computation is quite straightforward because we know from holography that we have to perform all possible reconstructions. And after computing the correlators, which are shown here, we can get the link order CFT data by comparing the result of the correlators with the corresponding superconformal clock expansions. And next to link order, the situation is much more interesting because we have to apply many constraints for the computation of the correlators. The first one is the construction of an appropriate answer. And to do this, we draw intuition from the Witten diagram expansion of the correlators. So at this point, we don't explicitly compute the Witten diagrams. We just use that we know which Witten diagrams contribute. And then from this, we can tell that at next link order, the answers should be constructed in terms of logarithms and rational functions. We also impose crossing symmetry, which is a symmetry under the exchange of points 1 and 3, and breaking symmetry, which is a symmetry under the exchange of points 1 and 2. I mean, it's a little bit more subtle than this, but essentially it's this. Furthermore, we impose consistency with the OPE, which is basically a consistency between the correlators and the superconformal expansions of the correlators. And this imposes boundary conditions on the correlators when the cross ratio goes to 0 and when the cross ratio goes to 1. And finally, we impose a dynamical constraint on the normal dimensions of the operators that comes from the fact that the more irrelevant the interactions at next to in order in the dual operator, the greater it should be the growth of the anomalous dimensions of the unprotected multiplets that are exchanged to the OP in the limit of large anomalous dimensions. So, given the similarity of the dual action in our case, with the dual action in N-equals force via Mills and ABGN cases, we impose that at next in order, these anomalous dimensions of unprotected multiplets should scale in the limit of large scaling dimensions as delta squared. Additionally, we impose that for the supermultiplets that are shared between the displacement and the tilt of E, the anomalous dimensions should be the same. So, by applying all these constraints, we managed to obtain the next to in order correlators for the displacement and the tilt supermultiplets up to 2 constants that are not fixed by the bootstrap procedure. And then, by comparing with the superconformal expansion, we managed to obtain the next to in order CFT data. So, we also performed an holographic check of this bootstrap computation, which at leading order comes from these disconnected Witten diagrams. At next to in order, we computed these Witten diagrams, and I want to stress that here we get exchange diagrams that are not present in the N-equals force via Mills and ABGN cases are new for these ADS3 CFT2 setups. So in the end, we computed these Witten diagrams, and we obtained that the bootstrap result precisely matches the Witten diagram expansion. And moreover, this Witten diagram expansion gave us an holographic interpretations for the coefficients that weren't fixed by the bootstrap procedure. So here we see that these two coefficients that weren't fixed by bootstrap are expressed in terms of the string tension, the ADS radius, and this bar theta parameter that interpolates between backgrounds, pure and non-round backgrounds, and pure Schwarz backgrounds. So let me now move on to the third part of the talk, which is the description of the integrability properties of line defects in the MGM theory. So one of the first steps forward in this in the integrability description of operators in the MGM theory was this result, which says that the matrix of anomalous dimensions of single trace operators can be identified with the Hamiltonian of an integral and periodic spin chain. The main feature of this spin chain is that it is alternating, and this means that we have two distinguished sides. So, for example, for the vacuum state, we get that the vacuum is identified with this operator, which is traced to the C1, C bar 2 to some power. And here we see that we have the sides given by the C1 fields and the sides given by the bar C2 fields. So when considering excited states, which are called magnons, we can get impurities that propagate on the C1 fields. These are type A impurities, or we can get impurities propagating on the bar C2 fields, which are type B impurities. One of the main motivations for our work is that in MGM, also in Mills, we can use the symmetry of the spin chain, which in this case is SU2/2, to almost fully fix the dispersion relation of magnons. But we see here that we get this H function of the back coupling, which is not fixed by the symmetries of the spin chain. And computing this H function is very important to all loops, because it percolates in every integrability-based result that we get in the theory. So to compute this, we can follow the same steps that were followed in Mills, which are essentially to compute the same observable at all loops, both from integrability and from another method, then to compare the results. So, for example, we can first compute the Kasparov dimension of the theory using integrability, then study the small angle limit to get what is known as the Bremsstrahlung function from integrability, and then compare with the Bremsstrahlung function, which was the same result for the Bremsstrahlung function, which was computed using supersymmetric localization. The comparison between these two results gives us, or should give us, the all-loop interpolating function of MGM, for which a current proposal exists thanks to Kolya-Gromov and Sisov, their paper some years ago. So in this thesis, we focused on this first step, which is the computation of the Kasparov dimension from integrability. So the first thing that we did was to study how anomalous dimensions of insertions along Wilson lines, in particular the 1/2 EPS Wilson line of MGM, could be described using integrability. We found that the matrix of anomalous dimensions of insertions along the 1/2 EPS Wilson line is identified with the Hamiltonian of an integral and open spin chain. In this case, it's open because of the presence of the Wilson line. In this case, the vacuum state is given by the insertion of this off-diagonal operator, which has an odd number of sides. And I want to stress that this vacuum state means that now the spin chain has SU1/2 symmetry, and this is in perfect agreement with the string theory prediction. In this case, the excited states are again type A and type B impurities, which propagate on this off-diagonal block. Given the similarity of this off-diagonal block with the periodic vacuum state, we get that the scattering matrix for the magnon is the same as for the periodic case. But now we get a reflection matrix for the reflection of magnons against the boundaries of the spin chain. And we computed this reflection matrix using the SU1/2 symmetry of the spin chain and perturbative expansions. And we got that these constraints fix the reflection matrix almost fully to be of this diagonal form. I want to stress that this reflection matrix satisfies the boundary Yang-Baxter equation, and this is a strong indication of the integrability of the problem. But the symmetry doesn't fit these overall phases, which are called dressing phases, which are these R0A and R0B factors. And to compute them, we derive a crossing equation for the dressing phases. Here the x's are Sakowski variables, and sigma is the Weiser-Eden-Staudlacher phase. And we gave an all-loop proposal for these dressing phases. And let me just stress some interesting properties of this proposal. So we get that we have the appearance of this dressing phase for the Wilson lines of n equals force by a mean theory, but now with the square root. And we get also this extra factor for the type A impurities, which accounts for boundary bound states that are only present for type A magnus. So I want to remark that we check the consistency of this all-loop proposal with weak and strong coupling expansions, perturbative expansions. So let me now discuss how to compute the cusp dimension of the theory using integrability. But first, let me introduce what is the cusp dimension. So if we consider a Wilson loop with the cusp, the presence of the cusp introduces divergences in the expectation value of the Wilson loop, which cannot be renormalized by the renormalization of the coupling constants of the theory. And instead, we have to introduce this zeta cap renormalization factor to the renormalization of these divergences. And this introduces the cusp dimension gamma cusp via this formula that we see here. So to compute this from integrability, we could consider the insertion of the vacuum state at the position of the cusp, and then study the vacuum energy of this vacuum state at arbitrary values of the length of the state. Then, taking the limit of no insertions at the position of the cusp, we recover the cusp dimension of the theory. But I want to stress that here we need to compute the vacuum energy for arbitrary values of length, particularly for finite values of the length. And this can be done by a method that is known as boundary thermodynamic better answers. This method was initially proposed by Samologico and then by Leclerc and collaborators in the 90s. And it's based on the fact that we can consider a theory with open boundaries and infinite temperature, which is a physical theory. In this case, the partition function can be safely approximated with the energy, with the exponential of the energy of the vacuum state. And then we could perform a double Rig rotation to get a theory which is known as the mirror theory, which has periodic boundary conditions and infinite size. In this case, now the partition function is mapped to a transition amplitude between two boundary states, which, as Samologico told us, can be expressed in terms of the reflection matrix of the integral theory. So in the end, we get that after the double Rig rotation, the vacuum energy of the system can be expressed in terms of these Y functions, which are the solution of a functional system of equations known as a Y system, which can be equivalently written as a T system of equations. So our proposal is that we can use the same Y system as for the periodic spin chain for the open case, but assuming different asymptotic and analytic boundary conditions for the Y functions. And this is based on the fact that if we look in the literature, we can often find examples where when going from periodic boundary conditions to open boundary conditions, usually the Y system doesn't change, and what changes are the asymptotic and analytic boundary conditions of the Y functions. So in order to test this proposal, what we did is to compute the one-loop cusp dimension from these boundary TBA equations. And we did this by computing a leading rapid correction to the vacuum energy from a Luxor formula. So the Luxor formula basically represents the exchange of two particles between the boundary states, and is this formula that we see here for the Y functions. And in the case in which these Y functions get a double foil, this is interpreted as the exchange of a single particle between the boundaries. So we computed these formulas, in particular for the fundamental representation, and then we used the Y system proposal to get the Y functions for arbitrary representations. And here, these T functions that we see in this formula, which are highlighted in red, We computed them using the proposal of bajo collaborators, which says that the T-functions of a system with SU1/2 supersymmetries can be computed from the T-functions of a system with SU2/1 supersymmetries, which were already known in the literature. So then, summing all contributions, we managed to recover the value of the one-loop Kasparov dimension that was previously computed by Grigol and collaborators from a Feynman diagram expansion. So now I will move on to the fourth part, which is the description of integrating net geometries in the MGN theory. So let me first introduce how can we construct the MGM amplitude geometry, which is the geometry that gives us the integrants for scattering amplitudes or loop scattering amplitudes, so 3 levels of scattering amplitudes in the MGM theory. So we can construct this geometry by taking the n=4 super mil amplitude, which I showed you before in slides, and then performing a change of sign, the constraints, and by imposing these symplectic constraints that we see here over the external kinematic data and the loop momenta. So, as shown by Sophia, collaborator, again in AVGM, we can express the logarithm of the scattering amplitude in terms of negative geometries, in particular in terms of bipartite connected negative geometries. And by bipartite, I mean negative geometries in which, after assigning a direction to each edge of the graph, each node is either a source or a sink. So, for example, here I show you the first 3 percurative orders that were computed by Sonki and collaborators for the 4-point negative geometries. What we did with Johannes and Shun-Kim Sang is to integrate all but one of the loop iterations over these geometries, and also in the 4 loop case, to get the integrated negative geometries. So at 4 points, the first thing that we notice is that dual component symmetry constrains the integrated results to take this form. So we see that after performing all but one of the loop integrations, we get a parity even term given by this f function, and a parity odd term given by these g functions, where here this Z is a dual conformal cross ratio, and I'm using capital X letters to denote the 3-dimensional coordinates in 5-dimensional notation after the embedding into a 5-dimensional icon. So using direct integration, in particular using iterated Feynman parametrizations, we computed the integrated results up to 2 loops, and we obtained the results that are shown here, where here this H is a transcendental weight 2 function. And then we perform the 3-loop integrations over the 4-loop negative geometries to get the 3-loop integrated negative geometries. So at 4-loop, we get these 3 types of contributions to the negative geometries. We get ladder diagrams, we get star diagrams, and box diagrams. And I want to stress that these box diagrams are the first loops of loops diagrams that we get in the AVGM theory. So to compute these integrated results, we use the method of differential equations proposed by Johannes some years ago. And essentially, the main steps that we followed were first to take the limit in which the unintegrated variable goes to infinity, because this allows us to use 4 particle kinematic variables. Then we found a basis of master integrals to expand the integrals that we wanted to compute. We constructed a system of first-order differential equations for these master integrals, and we took these differential equations to the canonical form. And by canonical form, I mean a form in which the epsilon dependence of the differential equations is factorized. And here, epsilon is the parameter in dimensional regularization. And finally, we solve the differential equations by imposing consistency conditions on the solutions. So this allowed us to get these final results, which in the end we see that are quite simple after iteration. So let me now discuss some properties of these integrated results. And I want to remark that studying these properties is useful towards possible higher loop bootstrap computations of iterated energy geometries. So first, we noted that the iterated results have a uniform transcendental weight. So F as order 2k plus 1 and G as order 2k have a transcendental weight 2k. The leading singularities of these results, and by leading singularities, I mean the rational functions that multiply the transcendental functions, are surprisingly simple in the limit in which the unintegrated variable goes to infinity. So they belong to this set of only 3 possible options. And finally, there are very interesting sign patterns for the integrated results, as we see here. To put a little bit of context, recently, last year, Johannes and Prashant Raman showed that many amplitudes and amplitude-related objects in many theories satisfy complete monotonicity properties, which are like a generalization of these sign patterns. So it would be interesting to understand further the origin of these properties in the integrated energy geometries. So finally, let me discuss how to compute the Kasparov dimension of the theory from these integrated energy geometries. So to do this, first we use the all-loop proposal given by Pedro and Colegromo some years ago, which states that we can compute the all-loop Lagrange Kasparov dimension of ADJM from the n equals 4 superior Mills Kasparov dimension, and then using the all-loop proposal for the H function given by Gromo and Siso, we get this expansion, this coupling expansion of the Lagrange Kasparov dimension of ADJM. And from this, we see that computing the Lagrange Kasparov dimension provides us with a very nice way to test this all-loop proposal for the H function given by Gromo and Siso. So now to get gamma cast from the integrated energy geometries, first we use this expression for the logarithm of the back expectation value of a tetragonal Wilson loop with light edges, whose lean divergence is expressed in terms of the Kasparov dimension of the theory. Then, using the duality between this 4-point Lagrange Wilson loop and the 4-point scattering amplitude in AVGM, we managed to derive this expression for the L-loop contribution to the Kasparov dimension of the theory in terms of these functionals that act on the F function and the G function that defines the integrated energy geometries of AVGM. Computing then the action of these functionals over arbitrary powers of the cross relation, which look like this formula that we see here in the corner, and then applying a Taylor expansion on the integrated energy geometries, we got this direct computation of the four-loop Kasparov dimension of the theory, which completely agrees with the all-loop proposals for gamma cast and for the H function, in particular in the case of the H function up to the order lambda to the 4. So let me now conclude and give some future directions. So in this thesis, we applied analytic conformal bootstrap methods and integrability techniques for the description of line defects in ADS-CFT dualities, and we studied the higher finite integrated energy geometries that emerge from the positive geometry description of amplitudes in the AVGM theory. So first, we found that there is a very vast variety of BPS line operators in the ADS-free CFT2 dualities. We applied analytic conformal bootstrap methods at next to leading order electron coupling for the description of correlators along 1/2 BPS line defects, and we found perfect agreement between the bootstrap computation and the Witten diagram, holographic Witten diagram computations. Then we found further evidence for the integrability of the 1/2 BPS Wilson line defect of AVGM. For this, we constructed an appropriate vacuum state and the all-loop reflection and scattering matrices for the speed chain. In the case of the reflection matrix, we proposed all-loop dressing phases via a crossing equation, and we found that these proposals perfectly agree with weak coupling and strong coupling expansions. Moreover, we propose a wide system of equations for the angle-dependent Kasparov dimension, and we check this proposal for the wide system by reproducing the one-loop perturbative result. Finally, we also computed the 4-point integrated net geometries of ABGM at up to 3 loops. And for this, we used either direct integration or the method of differential equations. We studied the properties of these integrated results, and we found that they satisfy uniform transcendental wave. They have uniform transcendental wave. They have very interesting time pattern properties, and moreover, the link singularities have a surprising simplicity. We also gave a prescription to compute the likelihood Kasparov dimension of the theory from the integrated net geometries, and we used this prescription to obtain a direct for-loop computation of the Kasparov dimension. So it would be very interesting to study the application of analytic conformal bootstrapping techniques in the line at higher points. And this is something that we are currently doing with Diego and Ignacio Salazar-Landea, in particular for the 5-point case in ADS-3CFT2. It would be also interesting to study the application of analytic conformal bootstrap techniques to setups with less or even without supersymmetry. For example, to the case of the 1,6 BPS Wilson line of ABGM, which is invariant under only 2 Poincare supercharges. Moreover, another problem would be to go beyond Maxwellian order in ADS-3CFT2 in the application of the analytic conformal bootstrap methods. And this will allow us to avoid the explicit computation of loop within terms, which are very difficult to compute with current methods. And for this, we could follow the results of Ferrero, Meneghelli, and Briard and Meneghelli in N=4 square means and ABGM. For the case of the integrability description of line defects in ABGM, it would be very interesting to try to find an exact all-loop solution of the boundary TVA equations in the small angle limit, because they will give us an integrability-based derivation of the Venezuelan function. And for this, we could follow the steps given by Polyagron and Siever in the N=4 square means case. It would be also interesting to try to solve the boundary TVA equations at 2 loops and see if we can match the 2-loop perturbative results for the Kasparov dimension of N=4 of ABGM, which was given also by Grigol and collaborators some years ago. And for this, we should iterate the boundary TVA equations following, for example, the procedure by Diego and collaborators of the N=4 square mean theory. We could also try to see if one can propose a quantum spectral curve for the Katz-Wilson line of ABGM, following the similar proposal for the Katz-Wilson line of N=4 square means by Guillermo and the Kovic Maslow. And regarding the integrated net geometries, it would be very interesting to see if one can bootstrap these integrated net geometries at higher loops using the properties that we found. Following, for example, recent developments by Johannes and collaborators, for example, for the bootstrap of the two-loop 6-point integrated net geometries in N=4 square means. It would be also interesting to try to understand the positivity properties of integrated net geometries both in N=4 square means and in ABGM. And this is something that we are currently doing with Johannes, Adolfo Hilario Garcia, Elia Mazzucchelli, Rajan Raman, and Jaroslav Trinka. We are trying to understand these positivity properties from the point of view of the geometric description of these observables. And finally, it would be nice to see if we can compute these integrated net geometries at higher points, in particular in the ABGM theory. So, thank you very much.
Okay, Martín, gracias. Felicitaciones por la presentación. Now we are going to pass to the question from the jury. Silvia, it's your turn, then Rojas, and then Vieira.
Okay, thank you very much. Well, first of all, congratulations, because you did an impressive amount of work. And the thesis is very well written, so I really enjoyed reading it. Okay, so I have a couple of questions that came out listening at your presentation, plus some questions about the thesis. Concerning the first set of equations, I'm curious to know better about the role of these. I mean, I'm sorry, let me first of all saying that I'm now considering your work about ADS3, CF2. Okay, so you know, what you did in order to find defects in two dimensions. And there is this theta which interpolates between pure Ramond and pure Neveu-Schwarz string solutions. So if you can comment a little bit more about the role of this theta, and in particular if there is an holographic interpretation of this theta from the conformal theory point of view.
Okay, yeah, it's a very, very good question. I don't really know if there is an holographic interpretation from the CFT point of view of this bar theta parameter. Yeah, for example, for the case of these defects, I think they shouldn't be strictly Wilson lines in the dual CFT because you get a different amount of flux because of the tilt angle. So I think there the tilt angle plays a role in the CFT, but I don't know a precise interpretation of this angle in the CFT.
Mm-hmm. Okay, and regarding your calculation of Witten diagrams, still in the same context, you did Witten diagrams to confirm your findings. And there the question is, at a certain point you might, sorry, an advice for the future, you should put numbers on the slides.
Sure.
It's easier to refer to the slide number. Where there were Witten diagrams, some drawings. Yes, here. So you mentioned that in this case you have these exchange diagrams which are not present in n equal to 4 super JMs or a BJM. Can you give me an idea why in this case this happens and not in the other cases?
Yeah, I mean, this is because in this case, one can consider the coupling of the string to the Neveu-Schwarz field. Precisely this coupling is not present in the n equals 4 super. In this case, it's an ABGM, and it gives us 3-point vertices, the dual effective string theory action. So these 3-point vertices give rise to these exchange diagrams.
Okay.
And very interestingly, this is precisely a reason of why we can consider, for example, 5-point correlators in these backgrounds, because we get these 3-point vertices that are not present in ABGM or in West Coast mills.
Mm-hmm.
And therefore, in those cases, we'll have to go to 6 points after 4 points.
Okay, and you know, from general overview of this part, do you think that one could grasp some clue about the structure of the dual conformal theory, or it's totally hopeless?
Well, I mean, I think perhaps in the case of pure Ramond flux, I mean, there is this proposal that the dual theory should be the IR limit of the Higgs branch of the D1, D5 system. And then there is some kind of Lagrangian description in that case. I mean, it's not easy to perform the RQ flow to the IR, but perhaps doing some supersymmetric localization studies, one could get some results from this Lagrangian description in the UV. And maybe that could give some intuition on the structure of the theory, at least in the pure Ramond case.
Okay. Mm-hmm. Good. Still on the same part, you did your booster calculation setting this big omega equal to pi over 2 in order to get the, let's say, ADS3 cross S3 cross T4 limit. Is there any reason why you could not do it for a generic omega? Is it too difficult? It's just a technical problem?
Well, I mean, in that case, the group is a bit more involved in some sense, because you get this omega parameter that enters in the algebra. And for example, I mean, at least we are not sure whether, I mean, to derive the superconformal blocks, we use the existence of a topological sector for the algebra. And for this, key point is that the displacement supermatrix is 1/2 EPS. And in the case of arbitrary omega, the displacement supermatrix is 1/4 EPS, and we are not sure whether the topological sector ideas could be still be useful to derive the superconformal blocks in that case. And this is a very key point in the bootstrap computation. But perhaps there is some way to go around this and perform the bootstrap in that case.
Okay, then do you have your thesis close to you?
Yeah,
No,
I think it's in the computer name.
Because I have a few questions about the thesis. Okay, so the first one is page 29. I have also to recollect where we are. Okay, so this is about the 1/2 EPS with online in a BJM. Yes. Analysis of fluctuations. Okay, you did get 3.27 by specializing what you find in Appendix A.
Yes.
In particular, equation A3, bisecting, I guess, D equal to 1 there, because you were considering ADS D plus 1 solutions, and then you said D equal to 1, and you get 3.27. Can you tell me why you did set D equal to 1 in this case?
Because, the dual string defines an ADS2 geometry. So we are considering fluctuations over the dual string. And then these scalar fields live in an ADS2 geometry. And therefore, we have to set D equals 1 in this case.
Okay,
I don't know if this answers.
Yeah, yes. Then page 57.
1 second.
What about it? Page 57. Here we are. Yeah, equation 4.93.
Yeah.
Yes. Okay. This is, of course, true, assuming supersymmetry is not broken at quantum level. Do you have any comment about that? Because, there are situations where supersymmetry, unfortunately, gets anomalous contributions at quantum level.
Yeah, to be honest, we didn't study whether there are some anomalies in this case. Yeah, we assume that supersymmetry holds also in quantum level in this case.
Yeah, it would be, I think, a bit of disaster, right? If supersymmetry were to be broken.
Yeah, hopefully.
I don't know. I never thought about what happens in the bootstrap program in this case. But okay, the answer might be that, for sure, supersymmetry becomes anomalous in the weak coupling expansion when you do perturbative approach. And this is because, the perturbative approach necessarily implies a breaking of conformal invariance, and conformal invariance implies breaking of supersymmetry. In the bootstrap program, you are assuming to do things exactly, no perturbation theory, so presumably this is something which is reasonable to assume. Okay, fine. Yeah, about, then even without referring to the right page, about the braiding symmetry that you have when you compute scattering amplitudes. Can you tell us what it is, what is the physical meaning of this symmetry, or the physical origin of the symmetry, is just a mathematical property?
No, as I said, it's basically the exchange of points 1 and 2. If you consider this exchange of points 1 and 2, you get that the cross ratio transforms following this formula that was here. And then if you use this identity 4.138 for the superconformal cross ratios, you can derive that using we are assuming the fact that a linear order with the some anomalies, some CFT data vanishes and some CFT data doesn't vanish. In particular, the one that doesn't vanish is where the anomalous dimensions and the Earth symmetry quantum numbers are either even or odd, or both even or both odd. So we are assuming that this holds also at next ring order, and assuming that this identity, we get these grading constraints. But as I said, I mean, it's essentially with some subtleties. I mean, the subtlety is this change in the logarithms, which comes from this mathematical derivation from the identity of the superconfirmed block. So, but it's essentially this exchange between points 1 and 2.
Okay. Okay, and then this is just a comment, page 128. You mention the self-duality of the ADS5 cross S5 string and the T-duality, which allows to exchange conformal and dual, super conformal and dual super conformal invariance, and therefore scattering amplitudes with Wilson loops. Which kind of T-duality is this?
I mean, it's a T-duality of the ADS 5 times 5 background.
But is it the ordinary T-duality or some?
I think it's a fermionic T-duality usually, right?
Sorry?
I think usually it's referred as a fermionic T-duality, right?
Yeah, indeed, it is. Yeah, this is quite important. Yeah, it should be fermionic T-duality. Okay, so, well, I think I've done because I had a few other questions, but you answered already during your presentation, so that's fine. Thanks.
Thank you. Thank you very much.
Great, thank you very much, Martín, and congratulations again, as Silva was saying, it's very impressive work. Yeah, congratulations for that. And so, okay, my questions are, I think they're very naive, basically due to my ignorance, but at the top. So, okay, so the first one that I have is, but if I remember correctly, the gas phenomenon dimension in the Nichols first agreement was always positive for all values of the coupling. I think it was Basso and Korczynski.
Could be.
Do you know if this is, no, the question is, do you know if this is true for APG?
No, I mean, in fact, I have that for the border is a -5 to the fourth.
Right.
We see here that we get the purple, the tulip order is 1, and then we get the -5 squared. So it's kind of
Between, yeah.
I don't know.
But I think in any but for also, you also have, you know, like an unpredictable, but you sum it all up. I think Basso and Korczynski showed that it always gives you a positive number. It was kind of puzzling why it was.
Okay. Yeah, I don't know. Perhaps, I mean, perhaps using this result by Basso and then introducing its old proposal for the H function, one could study whether this also generalizes to everything. But yeah, I don't know.
Okay. Thank you. At the beginning, when you mentioned that the status of, I think was in the case of APGM, even in N equals 4 superior minerals, that competition for N equals 6 was still, you know, not done yet. Then you're
yeah. You mean the table
for 6 points. Yeah. So, for example, it's what I understand. I think that they did it for, you know, the N for large and the N polygonal group, and using ADCFT. Would that help you? For the case of
6 points, you mean?
Well, for APGM. I don't know if
but you mean they can be the amplitudes for arbitrary points.
Right, and they took the N going to infinity. I mean, the number of points going to infinity. I remember, for example, for the BTS answers, by doing that, we realized that the BTS answer had to be correct, for example.
Yeah.
And for ABM, I know that there's also like a.
There is like an BDS proposal in every gen. Yeah.
Yes, I was found.
Yeah, the only article of Cecilia. Yeah, I don't know. One could use that to extract information about the 6 point, maybe. But if you take the n going to infinity, I guess maybe going to 6 point is, but yeah, it would be, I don't know. Yeah. Maybe to something, maybe.
Because yeah, if I remember correctly, it was the BDS. Using this computation, they realized that the BDS had to be corrected at 6 points already.
Yeah, okay. Yeah, I mean, in the case of amplitudes, it's a bit more subtle, I guess, LGM, because you have this fact that the helicity structure of the amplitude depends on the number of particles. So 6 points, you get the next one HV amplitude, 8 points, you get the next one HV. That's very different to the NX4. But yeah, it could be like.
Also, and related to that, what the status is for the sort of BDS exponentiation for these APGM? Is that set already?
I mean, there's this proposal, as you said, by Leoni. I think Silvia are collaborators, but beyond that, I think there's not much BDS as far as I know. Yeah.
Yeah, again, I have just very naive questions. Also, if I remember correctly, is it true? This could be wrong. But is it true that APGM gets enhanced for n equals 8 supersymmetry for the case of n equals 2 H2? I mean, SU2.
Yeah, you get this KLG. K equals 1, you get this KLG theory.
Would that help? I mean, I know you want to lower the supersymmetry, but in this case, since you have more supersymmetry, would that help you somehow? Or?
To bootstrap, I mean, 6 points. I don't know, because I mean, in Eagles first means you have more supersymmetries than in ABGM, and still probably an Eagles 4. But yeah, we.
Yeah, the last question that I had was actually the one that Silvia had, that why those within diagrams were absent in the Eagles 4. But
yeah, that's
nobody
the
answered that.
presence of the charts.
Okay, yeah, I think.
Thank you.
Thank you.
Hello. So I guess I go next, right?
Yeah.
Hi, Martin.
Hi, good.
So very good. So first, congratulations on the thesis. I was very impressed. So it's really a very impressive thesis. I think it's also a very useful thesis because you managed to work on many very different topics and survey them very well, but connect them very well as well. So I think if you have a student that is super expert in amplitudes but knows very little about integrability, this is a very good resource because they will feel very at ease in the amplitude part, and then they will really benefit from the connections to the other parts. And that works also for an integrability student that wants to learn about amplitudes. So I think the fact that you managed not only to put the topics that you worked on that are very different, but to connect them nicely, I think it's a great value. So I think, and I noticed that you did not just copy paste the papers, at least as far as I could tell, that you really tried to connect things. And I think the result is very good. A minor comment I would just suggest is at the very end of the introduction to just put a list of your papers. Right now, it was a bit, just to say, during this thesis, I wrote these 5 papers, like you did in the presentation. It's really great. Congratulations, and congratulations on managing to learn so many hard things and not only learning them, but going and producing really state-of-the-art results in many different fields. So let me ask you a few questions. So some are just my confusions that I did not manage to understand. So at some point, let me start with the things that I understand the worst. So you wrote some smearing of some Wilson. So is there an equation for that function G somewhere? Maybe I missed it. You wrote some function G. What is that G? Where is it?
I mean, basically, we we include that. I mean, you can, in principle, take an arbitrary weight function, but in the end, in all the cases that we studied, we take G to be constant, to be a uniform mean. But in principle, I mean, you could take an arbitrary constant and preserve for symmetries. Yeah. I mean, most importantly, we take the G to be uniform, to be just constant when we study fluctuations because if you take G to be constant, then the fact that you have a uniform mirroring means that at the level of the fluctuations, for example, at the level of scalar fluctuations, performing uniform mirroring is setting this. You know that you have these alpha and beta modes for the scalar fields. The alpha is the leading mode in the boundary. So setting G to be constant means that you have to set alpha dot. You have to fix alpha dot in the boundary. Otherwise, if you have more involved G functions, this boundary condition for the fluctuations could be a bit more involved. But yeah, in principle, at the classical level, to preserve for symmetry, you can take G to be arbitrary.
Well, let me tell you why I'm confused. I'm confused by the following. Normally, when we put a source that is delocalized in space, right, we integrate over where the source is, right? So we put like a Wilson loop, for example. It's exponential of an integral of where we put the source, right? Or if I put a source delocalized in space-time, it's exponential of something integrated. We don't integrate outside. We don't make a linear combination of fields outside, because if we did, that would be like a quantum superposition of things, and then it will be dominated by one configuration. So I'm confused by this weight being an integral outside this partition function. Why isn't this dominated by one classical solution that is the saddle of this average? Why is this mathematically the right thing to do and not the more conventional thing where the average is in the exponent?
That's a good question. Yeah, I think in principle there is the freedom, yeah, to perhaps to put the average in the exponent.
No, but I would not say.
Yeah,
I would not say. Sorry, it's not freedom, right? If I do a sum, if I do two different processes, like
it's not a freedom. Yeah.
One dominates, right? So if I do,
I think that, I mean, putting the integral overall is because, I mean, in some sense we are integrating on the boundary conditions of the fluctuations, and these boundary conditions are on the partition function overall, right? So that's why we put it the integral overall and not in the exponent of the exponential, because we want to average between boundary conditions.
Okay, so then my confusion is I integrate over boundary conditions. So for each boundary condition, I have a different classical action, right?
Yes.
So why don't I then do a saddle point to figure out which classical condition dominates? And that's the only one that I care about.
Yeah. Yeah, that could be. Yeah. Yeah, to be honest, I haven't thought about it, but yeah, it could be, I guess. I mean, in some sense, yeah.
But I'm confused what you mean it could be. So is this formula then correct or not?
I mean, I expect it to be correct, but it could be that you can take the sub points. But yeah, I don't think so, because I mean, the smear strings preserves some smaller subset of supersymmetries of the Dirichlet string in general. I mean, except for the one part in this case. So if you take the saddle point and you only get the contribution from one of the strings, I guess you should always get that the smear string preserves the same amount of supersymmetries of the Dirichlet string, right?
I believe that there is a bulk computation that corresponds to smearing something and doing another computation. I'm just wondering if that dual computation corresponds to this formula or to something else. I agree that you can probably find other boundary conditions that you call some smeared boundary conditions that preserve this or that supersymmetry and so on. That must exist for sure. That's what you did, right? I'm just confused about why I interpret that as an average of quantum computations. Maybe I do, but it's just I'm not used to this.
No, instead, I mean, we consider this average because we were integrating our boundary conditions for the fluctuations. But yeah, to be honest, I didn't thought about this fact that maybe you can take like a saddle point approximation and get only one contribution. I mean, I expect this not to get only one contribution because of what I said, that maybe this would imply that we are only preserving the 1/2 symmetries of the Dirichlet string. But I have to take a more deeper look, to be honest, to say this more with more precision.
Okay. Okay, so that was about smearing. I have another. Okay. So let me ask one question about this, the function h of lambda. Is there some physics in this relation between lambda and h of lambda? Is there something interesting? It's a complicated relation with some hypergeometric and so on. Do you think there could be some interesting physics there? Like, are there critical points I could identify, points where the relation between h and lambda develops some critical behavior, some power law, and could that indicate some interesting point in the space of couplings in ABJM and what could be its physical meaning or not? Or is it just a parameterization of the coupling? So do you think there's physics in the relation between h and lambda or not?
I mean, I believe that the proposal of Collier probably 99% is the correct one. And I don't know if there is any physics behind it. I mean, I wouldn't expect it, I guess. I mean, for me, it's just a way to reparameterize the coupling. Either you can take H or you can take like the top coupling, right? Because I also
that I don't know. It's my question, because I would suspect that probably there are quantities you compute from localization or from other things that are more naturally expressed in lambda and quantities that are more naturally expressed in H. And therefore, it's not so obvious that H is just a parameterization. Maybe for integrability, H appears, but for other things, lambda appears. I don't know.
Well, for example, I mean, in this case of the proposal between the relation between gamma cut in ABGM and gamma cut in N equals 4, I mean, then it's more natural to use H rather than the top coupling, right? Because it's just replacing the H of N equals 4 with the H of ABGM. So, I mean, it seems like at least in the context of integrability and gamma cuts, it's more natural to use H rather than the top coupling, I guess.
Of course, yeah, that I agree, yeah. Okay, so you don't think there is some physics there. But let me ask just a question. I should know this, but I forgot. Is there a cusp anomalous dimension in these ADS3 examples?
I mean, it's not studied yet. No. I mean, there's, as far as I know, there's no result about the cusp anomalous dimension.
Okay. Just probably a silly question, but you mentioned that you are studying 5-point functions in ADS3. I think you told me this once. I think once I asked you this, you said that in N equals 4, there's no 5-point function, you said, right?
Yeah, exactly. You have to go to 6 points after 4 points.
Is there a simple argument why in N equals 4 there's no 5-point function?
Because you can think about this in the strong coupling limits, then you don't get these 3-point vertices in the dual action, neither 5-point vertices. So you get 4 points at 6 points. Therefore, at least as far as I know.
But is that because you consider even operators? Don't you have odd operators in the theory? Can't you consider even odd goes to even, something like that?
You mean including fermions?
For example, some operators that are odd under disparity that forbids this term, right?
Yeah. Could be, yeah. To be honest, I don't know in the case of Permit. I mean, I haven't studied this too much.
Just wondering, it could be much simpler to
To go to an input form. I agree.
go to an input form and study all operators.
Yeah.
Still about that, is it possible when we compute these functions of the cross ratio, this f of chi's and so on that you explained, can we take a flat space limit?
Well, I would say probably they explode. Well, I mean, yeah, you have to take some kind of leading order because the coefficients of the bootstrap, which are like overall coefficients, not overall, but I mean, the f and h are proportional to the p coefficients that are not fixed by the bootstrap. These are directly proportional to the ADS radius, right? So you get like the ADS radius, I think, is factorized overall these f and h functions.
Yeah, but physically, I'm just imagining that I have ADS2, right? It's a big box, but there is a region in the middle which looks like flat space. So I should be able to, from these amplitudes of 4 points, in some kinematics, probably they are dominated by scattering happening in a small region inside ADS2, some kind of high energy scattering. And then I could use this small region to extract out of these results that now you have too many orders, right? Some kind of flat space S matrix in one of 2 to 2 particles. Do you think it's possible?
I don't know if it is possible. I think it would be very interesting because, I mean, if we study 5-point correlators, and then one could study whether these defects are integral or not, and that this could be like
I think even for 4 points, you could do it for 4 points, extract the 2 to 2 for many different external states, I guess, right? And try to see if this 2 to 2 in flat space that you would extract from it to see if it would obey Young-Baxter, for example.
I think it would be very interesting. I mean, as far as at least up to next to leading order, the dependence on the ADS radius is quite simple. I mean, as I said, I think it's an overall dependence. But perhaps when you go beyond next to leading order, it gets more involved and can get more like interesting.
No, but I think you have to be careful. You have to be careful because typically what happens is that, for example, when you study these amplitudes in Mellin space, you need to rescale the Mellin amplitudes as well with powers of the radius and then collect the leading ones in a flat space limit. It's not just about collecting powers that sit in front.
Probably you have to be careful with the limits.
So from each result that you have to each order, a part of it contributes to the flat space and a part does not.
Okay. I think it's very interesting.
So let me ask a last thing that is the topic that perhaps I was very curious to know more about. It was somehow something that it skipped me completely. This negative geometry stuff was super interesting. So let me ask you something. First, I was a bit confused. So how do I did not see the BDS result written anywhere, but you said that this quantity is almost the amplitude. There's one more integration to do, and then I get the amplitude, right?
Yeah.
So is there some, and then you also wrote that you can extract the cusp dimension as some 1 over epsilon square singularity when I do this last integration, right? So should I think that in the 1 over epsilon that you did not write, is there where BDS is, or am I being naive? I suspect I'm being naive, but.
I mean, how also the contribution from collinear divergences of the sublink 1 over epsilon, right? I mean, I think you should consider all the contributions in the epsilon expansion, right? To get the BDS expansion. I think you cannot stay only at the level of the league 1 over epsilon square term.
Sorry, can you repeat?
No, I think that you cannot pay only at the level of the 1 over epsilon squared term. You have to consider like the full epsilon, right? The function, or at least the 1 over epsilon also term that gives you the collinear divergence.
Let me tell you a bit why I was also confused. Because at some point from your thesis, I got the impression that this function f is like the ratio between the 4 points and an extra point and just the 4 points. Maybe this is a wrong impression, but I got the intuition that I should think of this f as like the Wilson loop plus an extra probe divided by just the Wilson loop, for example.
Well, I mean, in fact, in N=Mills, these intermediate geometries are interpreted as inserting a Lagrangian with the Wilson loop, taking the expectation value and then dividing by the Wilson loop without the Lagrangian.
Yes. So can you comment a bit on this division by? Because I agree that if you divide by, then yes, I understand that this object now doesn't have cusp dimensions because you divide by it.
Yeah.
What is exactly, how do I think of this division by? Is it then true that this is the quantity, it's the amplitude up to one integration, or it's something a bit more sophisticated than that because there is this division and so on?
No, I mean, to get the amplitude up to one iteration, you have to include this normalization, for sure.
So will we get BDS or no, because we divided by BDS and therefore
this is because you get that the duality between Wilson loops and amplitudes is at the level of the logarithms. So you get that the logarithm of the amplitude is dual to the logarithm of the Wilson loop, and that's why you have to divide them by them. It's because you are kind of like performing a derivative on the logarithm of the Wilson loop, and then you get a division by 1 over the Wilson loop. I mean, that part comes from there.
Okay, so let me try to combine what we have been discussing. So there are two possibilities that I don't know which one is the correct one in my mind. I would like to know. Will I get BDS if I carefully do this last integration, keeping all the 1 over epsilon terms, or no, because I divided effectively by BDS by dividing by this 4-point function, and therefore it's not about doing the integration more carefully? Which one is correct?
No, I mean, we are considering the amplitude normalized by the 3-level amplitude, but
no, 3-level, I don't.
I expect no, for sure you should get BDS after integration.
Okay, after integration in Z, I get BDS, which is a function of S and T, you say.
I mean, you have to integrate not over Z, but over the unintegrated points, or the full 3 coordinates of the unintegrated loop variable. I mean, over Z, it's like you are just performing a 1-dimensional integration. You have to perform a 3-dimensional, right?
Why? I mean, isn't the function just a function of a cross ratio?
Yeah, but the cross ratio, I mean, it's a function of this unintegrated loop variable. And okay, the amplitude is the integral of this unintegrated loop variable.
Okay, that's fine. But if it only depends on the cross ratio, the rest is just some Jacobian, right? I mean, it's...
I mean, probably it's just a simple integral overall, but it's not just the set integral, right?
So in doing that integral, if I do that integral, are you saying that if I do that integral carefully, I integrate some function that depended only on Z, right?
Yeah.
Now is the claim that if I do this integral carefully, I get this log S times log T, blah, 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 of BDS, or I don't because I divided by the 4-point function, which implicitly, if I regulate it, contains already this log S and log T.
No, I mean, I would expect that you get, I mean, you should get something that is coherent with BDS. I mean, for sure. Yeah. I mean, I haven't done it, but I will expect so.
Do you have a way of thinking about these quantities that are one integral away from being the amplitude? From a more amplitudes point of view, suppose I'm thinking just of scattering amplitudes. Do you think this kind of object is something I could expect to exist for?
Well, there is a very interesting duality that was found by Johannes and Dimitri Ticherin between these integrated netted geometries. I mean, in the case of conical chord, between these Wilson loop with Lagares and insertions, and all plus amplitudes in pure Young-Mills theories. So in that case, there is a very interesting like physical interpretation, or at least at the level of this duality between the integrated results and all plus amplitudes. But I think it's more like an interesting object to study and to because of these IR finite properties, they are interesting to work with them and to study how to compute them and how to bootstrap them, for example, and then try to extrapolate this to scaling amplitudes, right? Well, we get
For example, let me say something that probably is crazy, but we don't know how to bootstrap scattering in 4D gravity because of infrared divergences. We don't even know what an S matrix means. And we have similar problems with gluons, but less severe. But should I expect that perhaps, because I always thought that infrared divergences are a nightmare, but then I was reading your thesis, I was thinking, could it be that there is some trick that is only one last integration? Then I should not be that worried if it's just one more integration. So is that an object that is like a 2-2-2 gravity and amplitude up to one integration and that is infrared finite? Or that's...
to be honest, I don't know in the context of gravity. I mean, I don't know if this property that if you perform all but one of the loop integrations, you get a finite object is like a general thing, or I would expect that it's most probably a property of theory that have a geometric description in terms of positive geometries and negative geometries. I don't know if this is something that generalizes to arbitrary theories. But yeah, I don't know if in the case of gravity one can consider this. Perhaps, I mean, it would be very interesting.
Okay. No, anyway, it was very inspiring either way, yeah. So I think that's it. Thank you very much. Congratulations again.
Thank you.
Well, okay, if we are done with the questions, I'm gonna to stop the YouTube transmission. Voy a parar la transmisión de YouTube para todos los que nos están mirando por YouTube. Después vamos a volver para la parte final.
The president of the committee in Italy, but there is no president today, so I don't know.
Pedro, are you in Canada, Brazil, or somewhere else? No,
Right now I'm in Brazil. I'm in Brazil.
Where?
I'm in Principia, near the hotel, yeah.
Ah, okay. Everybody's coming in. La cámara.
Se conoce aquí. Sí, por eso. Por ahí tenemos que por camino
la pareja de
como bien. Como te decía,
Bien, cuando estén listos, pueden leer el acta, ¿eh?
¿Dónde está la colección?
Hay que decidir. Bueno, nada, solo voy a alguien tenía que leer el acta y me pidieron, así que siendo las 12 horas del día 11 de agosto del 2025, se reúnen los integrantes del jurado de tesis del licenciado Martín Lagares, de la carrera de doctorado, área física, de la Facultad de Ciencias Exactas de la Universidad Nacional de La Plata, integrado por doctora Silvia Penati, doctor Pedro Vieira y doctor Francisco Rojas. cumplimentada en el día de la fecha la defensa oral a cargo del licenciado Lagares. Los miembros del jurado califican el trabajo de tesis denominado Defectos de línea y amplitudes de dispersión en el contexto de la correspondencia ADS-CFT, bajo la dirección del doctor Diego Hernán Correa, como aprobado con mención especial. El trabajo de tesis, defectos de línea y amplitudes de dispersión. Bueno, paso a leer el dictamen, perdón. El trabajo de tesis, efectos de línea y amplitudes de dispersión en el contexto de la correspondencia de SSPT, fue presentado por Martín Lagares. La tesis abarca temas relacionados con los aspectos geométricos de las amplitudes de dispersión, así como los defectos de línea, tanto desde el punto de vista de la integrabilidad como desde una perspectiva de bootstrap. La tesis abarca 4 temas diferentes de física de altas energías, conectándose de manera hermosa en un trabajo cohesivo. Además, el trabajo realizado en cada uno de estos temas es de vanguardia y se llevó a cabo en colaboración con un conjunto diverso de colaboradores, demostrando gran independencia y madurez. El tesista desarrolló una exposición oral ordenada y clara, respetando el tiempo acordado, respondiendo con solvencia a las preguntas y demostrando manejo de la temática. A partir de la exposición oral, se logró una interpretación más integrada de las diferentes secciones que componen el trabajo de tesis. En base a lo expuesto, este jurado aprueba la presente tesis como aprobada con mención especial. Firman Silvia Perati, Francisco Rojas, Pedro Vieira. Para felicitaciones.
Congratulations.
¿Me escuchan ahí? No, por ahí no me escuchan por el sonido del coso. ¿Me escuchan ahí?
Sí.
Martín, ¿querés dar algunas palabras finales?
No, gracias a todos, gracias a Pancho por venir acá, gracias a Silvia, thank you to Silvia and Pedro for accepting me members of this committee. Gracias a todos por venir, una etapa muy linda y gracias y bueno.
Okay. Silvia, Pedro, do you want to say final words?
Still
No,
great,
once again,
congratulations.
I would congratulate just once again Martin. Just out of curiosity, Martin, do you know what you are going to do next?
Yeah, I'm starting a postdoctoral position in October at Queen Mary University in London with direct annals.
Oh, very good. Congratulations. Yeah.
Thanks.
That's great. Yeah. No, London is a perfect place. Yeah. You will have lots of people to discuss.
Yeah, I'm very,
topics and to learn much more.
I'm very happy. Yeah, thank you. Thank you.
Well, thank you very much, Silvia, Pedro, Francisco. It's a pleasure to be, an honor to be part of the jury with you. Gracias a todos también por estar ahí. Un día bastante raro para la tesis por la situación, pero hemos podido llevarla adelante. Agradecemos a todos por su predisposición. Doy por finalizado el acto del licenciado Martín Lagares, ahora doctor, ya. Y bueno, esperamos mañana no, el jueves 14, una nueva tesis de la licenciada Galicet. Thank you very much, Pedro, Silvia, y muchas gracias a los que nos están mirando. Hasta luego.
Thank you.